Okay, moving right along. Boat has some mass, it accelerates from there to there. Resistive force of the water does that much work. How much work does the propeller do on the water? Now, for this to be a really great problem, I would have to make a few more things explicit. But what can you probably assume here? Yes. But what can we assume that's directly relevant to our equation? No air resistance, sure. No other non-conservative forces that aren't mentioned. And one more thing. Yeah. So the boat doesn't sink, which means what? We can say our change in potential energy is probably 0. Yeah. That's what I was going for. Then our non-conservative forces, we've got resistive force of the water, work, propeller. So if we're considering the boat, this would not be work done by the propeller. So the propeller does work on the water. So the water does, technically the water is doing work on the propeller to push it forward. Newton's third law, propellers exert a force on the water, so the water exerts a force forward on the propeller, which does work. Oh, and then we can plug and chug. Yes, the total work done by non-conservative forces. And that comes out to about I'll call that 57,200 joules, rounding arbitrarily. Right. I'd like you guys to give 35 a shot here. So let's do this version just cause. Yunjung, what do we have for work non-conservative?
Friction.
Friction. So what should I write?
Negative mu k F, normal force times distance.
All right. What about this?
I did that at 0.
Okay.
And also no kinetic.
Okay. Then what did you have on the right side?
1/2 mv squared minus mg d sine theta.
Good. Oh, plus. That's important. And what is normal force in this case?
Mg cosine theta.
And what happens algebraically? Bye bye, bye bye, bye bye. And what did you get for mu k?
Negative v squared plus g times d sine theta over 2g cosine theta times distance.
Wait, say that again? Oh, you didn't say the 1/2.
Oh.
Okay. I was like, where's your 1/2 at? Plus, did you say GD sine theta?
Yeah.
Okay.
Over g cosine theta times d.
Sure. Yay! Hoorah. She said wherever her skier starts, she decided that was the zero potential energy. So then we wind up with minus a negative potential energy. You could just as easily say the initial is mgd sine theta and the final is 0. Yeah. Or delta. Yeah. Either way, as long as your equation is equivalent, it doesn't matter where you put that. Right. Yeah, so those are just some examples of dealing with non-conservative forces. Our last concept for the unit, power. Power is the rate of change of energy with respect to time, which is the EDP. The rate at which energy changes is the same thing as the rate at which work is done. So depending on the situation, you might want to say dW dt. Also, those are the same thing because a positive change in energy for the system will correspond to positive work being done on the system. If force is constant, we can just say power is equal to work over time without the calculus stuff. If we happen to be moving at constant velocity, there's an alternate version of this because work is equal to what? Force times distance. So that puts a d over t here. So if we're going at d over t is velocity, average, but if you're going at constant velocity, that's just velocity. So we can also say power is equal to force times velocity. That is another legitimate formulation of it if we are going at constant velocity. What is the unit of power? That was a statement. Watt is the unit of power. It sounded like a question. Okay. Which is abbreviated capital W. Hey, that's confusing. Capital W for unit, capital W for variable. Watt, work. All right. Based on the formula, what is 1 watt equal to? What? No. Based on the formula, using dimensional analysis. Watt is the unit of power. Thank you. And what was 1 joule?
1 Newton.
But what was a Newton? It was kilogram meter per second. So we've got, or kilogram meter per second squared, right? So kilogram meter times meter gives us meter squared per second squared with another factor of seconds. So our power is a kilogram meter squared per second cubed, which is why we have the watt, because that's a lot to say and write every time. Yeah. So Joule, the person, Joule the guy. Joule walked into a bar. It took him 1 second. Bartender says, "Hi, Watt." Anyway, because 1 joule came in a second. That's a lot. The Watt is named after James Watt, who invented the steam engine, or invented a more efficient steam engine, which kind of kicked off the Industrial Revolution. So good for him. In British units, they use horsepower, which is equal to 746 watts. I don't know whose horse that was that they decided was that in America, if you see like car commercials and stuff, they'll say this car has this many horsepower. Yeah, so the book has one or two things that are in horsepower, and you have to convert the unit. It's a tough life. So basically, for power, I can ask you any question that I've asked you about work, and then give you a time, and you calculate power. Or I can, the other way around, give you power and a way to figure out work, calculate time. So these questions about power can be just as complicated as anything we've done with work. So for example, like I said 34b, so referring to the boat from above, if the boat accelerates like this in 1.5 seconds, what power does the propeller exert? How would we figure that out? Yeah, power is just work over time. So we take that 5, 7, whatever it was, 177.6 divided by 1.5, and we get that's about 38,000 watts. Okay. A 65-kilogram student walks up a flight of stairs at constant velocity, raising his elevation by 4.5 meters in 5.3 seconds. How much power is he delivering? So, we can say work done by non-conservative forces is delta K plus delta U. What's delta K? 0. So the work done by the student is going to be mg delta y. So the power exerted by the student is going to be mg delta y over t, which is just 65 times 9.8 times 4.5 divided by 5.3, and we can calculate that. Which comes out to about 541 watts. Keep in mind that the calculus relationship also exists. I didn't put anything like that in the note packet, but if you're given where you can find an equation for energy as a function of time, then if you take a derivative to get power. This is your homework.